So how does this chemical weathering feedback affect the Eocene climate? Well, to think about that, we have to understand the longer cycles of calcium carbonate in the Earth today. Again, we think that on long timescales, the carbon dioxide in the atmosphere is regulated by the release of carbon dioxide from volcanoes, and then ultimately the conversion of that carbon dioxide to calcium carbonate that's buried on the seafloor. But on these long timescales, the calcium carbonate can actually be once again converted back into carbon dioxide by subducting crust beneath the ocean floor. When subduction occurs, when the ocean crust is subducted, when two plates come together, some of the sediment that sits on top of that is carried back down into the Earth. So some of the calcium carbonate that's buried on the ocean floor gets pushed back down into the mantle. When that happens, the calcium carbonate is heated up, and at least some fraction of it is turned back into carbon dioxide and released in volcanoes. So when you look at places like Mount Etna in Italy, or if you look at some volcanoes along the Pacific margin today where we think a little bit of calcium carbonate is being subducted, we see in those places a high emission of carbon dioxide from volcanoes. So there's some evidence that the subduction of calcium carbonate along with the ocean crust releases more carbon dioxide from volcanoes. So the interesting thing about the modern distribution of plates around the Earth is that most of the subduction is occurring around the Pacific, what we call the Ring of Fire. That's because North America and Asia are actually converging on each other, and so the Pacific is shrinking as the Atlantic is slowly increasing in size. If we go back 100 million years ago to the Cretaceous period, this was a very different time period where we see that there was still some subduction along the Pacific, but there was also subduction along an ocean that no longer exists, an ocean called the Tethys Ocean that occurs roughly where the Mediterranean was today. But this was a very different situation where the Tethys existed mostly in the tropics between what is now Eurasia and Africa, and also the Indian continent that was connected in the early Cretaceous with Antarctica and Australia. Over this time period, India and Australia moved slowly north as ocean crust in the Tethys was being subducted beneath Eurasia. One thing we know about the Tethys Ocean that occurred back in the Cretaceous and really ended when India collided with Asia is that it was full of calcium carbonate. If we look at the remnants of the Tethys Ocean today along southern Europe, in Italy and Greece, or in India, we see that all the sediments were full of calcium carbonate. That's not that surprising. The Tethys Ocean was a tropical seaway that was full of coral reefs and other calcium carbonate organisms. We think that the subduction of all of that calcium carbonate associated with the Tethys Ocean increased the amount of carbon dioxide coming out of volcanoes. So that back in the Eocene and in the Cretaceous, there was a lot more carbon dioxide released from volcanoes, and that this explains the higher carbon dioxide concentrations in the atmosphere. As soon as that subduction stopped and we switched from subducting the old Tethys to the modern Pacific, which has very little calcium carbonate, we went from a very warm climate to a very cold climate. And this fluctuation between subduction of calcium carbonate and subduction of ocean sediments that have very little calcium carbonate may be the cause for this very long 100 million year fluctuation in Earth's climate today. So this chemical weathering feedback that regulates the Earth's climate on long timescales will ultimately take care of the anthropogenic climate problem. Eventually, the carbon dioxide we release from burning fossil fuels will be converted to calcium carbonate. We just have to wait for it to occur. The problem is the timescale. Again, the chemical weathering reactions are balancing volcanic outgassing and occurring at about 1/10 of a gigaton a year. To get rid of all of the carbon dioxide released from burning of fossil fuels, we'd have to wait about 100,000 years for all of that CO2 to be converted to calcium carbonate. So the Earth system will be just fine. The problem is that we and all the other living things on the Earth have to manage through the next 100,000 years until the Earth system can correct itself. The Keeling curve, starting in 1957, really only gives a snapshot of what we're dealing with in terms of the carbon cycle on these different timescales. When we look at the carbon cycle, we know that there are large reservoirs of carbon, the largest being the ocean, with roughly 40,000 billion tons of carbon. And all of the reservoirs, the terrestrial biosphere, soils, the deep ocean, they're all exchanging on different timescales. And we know, for example, that the CO2 fluctuations we observe in ice cores from Antarctica, ranging from 180 parts per million during the glacial maxima to close to 300 parts per million during the interglacials, that these fluctuations, we think, are due to changes in the partitioning of the ocean and the atmosphere. What this means in terms of our picture of the carbon cycle is just that the ocean in its colder state held just a little bit more carbon dioxide, and that there was a little bit less in the terrestrial biosphere and in the atmosphere, and that this led to an overall drop in carbon dioxide in the atmosphere. On the longer timescales, when we see the large changes in temperature going back to the Eocene and associated changes in carbon dioxide in the atmosphere, we think that the cause of this is quite different. That this is not a change in partitioning between the ocean and atmosphere, but rather a large-scale change in the total amount of carbon in all of the active reservoirs. And we've talked about this in the context of long timescales in the carbon cycle and the release of carbon dioxide from the deep earth through volcanism and its return to sediments through the weathering of silicate rocks and the burial of calcium carbonate and organic carbon. All of these different timescales of the carbon cycle have been put together nicely by David Archer from Chicago, who in a series of papers with various colleagues tried to explain what is going to happen to anthropogenic carbon dioxide over the coming centuries, millennia, and even hundreds of millennia. These figures are from a paper that David Archer wrote with a colleague back in 2008, and it's a nice example of what we expect will happen to the carbon cycle over these different timescales. The first figure shows the emissions of carbon dioxide to the atmosphere from burning a fossil fuel, measured in billions of tons of carbon per year. There are really two lines to pay attention to. The thick black line, which is a scenario in which all of civilization releases 5,000 billion tons of carbon cumulatively, and the thick gray line that is a similar scenario but for only 1,000 billion tons of cumulative carbon emissions. One way to think about these scenarios is that the low carbon scenario, the 1,000 billion ton of cumulative carbon emission scenario, is really just about the minimum that we could imagine keeping human emissions under. If all the countries in the world got together and worked desperately to install renewable technologies and stop using fossil fuels, it might be conceivably possible to limit emissions to 1,000 billion tons of carbon. Today that looks incredibly unlikely, but it is technologically possible that it could happen. On the other hand, the high scenario, 5,000 billion tons of cumulative carbon emissions, is a scenario that's pretty much what would happen if the world went on a fossil fuel binge for the next several centuries. This is equivalent to basically using up all of the oil and gas reserves that we know about and all of the coal reserves, plus additional reserves that we would discover in the next few centuries. If that happened, we would emit cumulative emissions of about 5,000 billion tons of carbon. We could also get to this high emission scenario if we emitted only a few thousand billion tons of carbon from burning of fossil fuels, but additional carbon cycle feedbacks, for example, the drying out of the tropical forests or the release of carbon from soils in the Arctic, were to add to the total emissions. So you can think of these two scenarios as end members. The low one being what would happen if we did as much as we could to control emissions, technologically possible but extremely unlikely. And the other scenario being the one that would happen if we really continued to use fossil fuels in a very reckless way for the next several centuries and basically use them all up. Note that the scenario with lower emissions pretty much ends emissions sometime in the middle of the 22nd century, around 2150 or so, whereas emissions in the higher emission scenario, 5,000 billion tons of carbon, continues on till about 2400, and after that, emissions are at zero. So these two scenarios frame what is possible for the future. If we look at the outputs from David's carbon cycle model, what you see in these two scenarios is very interesting. First, if we think of the low carbon scenario, we can see that the carbon dioxide concentrations rise up to about 500 or 550 parts per million, and then start to subside, plateauing a little bit under 400 parts per million, but then staying there for a very long time. Note that the time scale on this figure is now changed. Instead of going from 2000 to 3000 AD, what it's actually showing is 2000 to 12,000 AD. So this is actually covering 10,000 years into the future. This is what David Archer calls the long tail of the carbon cycle. And it comes from the fact that even after the ocean has mostly equilibrated with the anthropogenic CO2 we've added to the atmosphere, that is, the ocean mixing has taken up all the CO2 it can hold, and the calcium carbonate dissolution has added some additional storage capacity by the ocean. There's still an additional residual tail of the carbon that we've added. Something like 10 to 20% of the CO2 we put in the atmosphere will remain there and can only be removed by the slow silicate weathering process. And that's what takes so long to come down. So even if we were to curtail the use of fossil fuels in the future and limit cumulative emissions to about 1,000 billion tons of carbon, which, as we'll see later in the course, is incredibly difficult to do, we would still rise to about 550 parts per million CO2, and then come back down and plateau around 400 parts per million, the current level in the atmosphere, and stay there for tens of thousands of years. The important point is that we're actually making decisions today that will affect the Earth for tens of thousands of years. If we were to continue to use fossil fuels for the next several centuries, much like this high carbon emission scenario, we would be returning the atmosphere to a state like the Eocene and leave it there for tens of thousands of years. Over those timescales, it's not clear that the Greenland ice sheet and even the Antarctic ice sheet could survive the warm conditions. This isn't going to affect us or our children or even our grandchildren very much, but it will profoundly affect every living thing on Earth, not just for a few generations, but for tens of thousands of generations. The oxygen isotope record from benthic foraminifera over the last 70 million years is an incredibly rich record of Earth history. It records all sorts of different events over this timescale: the waxing and waning of ice sheets, changes in the movement of continents, the opening up of the connections between different ocean basins. All sorts of other geologic events are recorded in changes in the Earth's climate over this timescale. But there's one event that's particularly useful in discussing how anthropogenic climate change will proceed in the future. This is called the Paleocene-Eocene thermal maximum, which occurred right here where this red arrow indicates at around 55 million years ago, the boundary between the Paleocene and the Eocene. Now, this event has a rich history over the last 25 years or so. It was discovered first in cores from ocean sediments in the Southern Ocean near Antarctica, and then scientists observed it all over the world. The Paleocene-Eocene thermal maximum is an abrupt warming event that occurs right around the boundary between the Paleocene and the Eocene, resulting in roughly a 6-degree warming of deep ocean temperatures. If we zoom in on this graph, what we actually see here, right around 55 million years, we see these different oxygen isotope records from 56 to 55 to 54 million years ago. And we see this abrupt warming that occurs in less than about 10,000 years, where temperatures went from around 9 degrees Celsius up to around 15 degrees Celsius, and then slowly came back down over the timescale of 1 to 200,000 years. Again, you see this in multiple records from different parts of the world oceans. Some additional evidence about this event comes from the carbon isotopes of benthic foraminifera, or the ratio of carbon-13 to carbon-12. Just like for oxygen isotopes, we use delta notation. So we talk about the delta C13, which is just the ratio of carbon-13 to carbon-12 in our sample normalized to a standard that our community uses. So samples that have positive delta C13 means that the sample has more C13 than the standard, and samples that have a negative delta C13 means that the sample has less carbon-13 than the standard. The carbon isotopes tell you something about the balance between sources and sinks in the carbon cycle. What we see right at the Paleocene-Eocene thermal maximum is that, coincident with the abrupt warming, we see a large drop in the delta C13 of the foraminifera. And we see this drop in carbonates from all over the world. Looking up close, again, what we see is a very abrupt drop, similar to the abrupt warming on the same timescale of about 10,000 years, followed by a slow increase back to the background levels over a period of 100,000 to 200,000 years. The delta C13 changes by about 2.5 to 3 parts per thousand or per mil over this timescale. This map shows where the PETM delta C13 excursion has been observed in ocean sediments and in terrestrial sediments all around the world. And you can see that this really is a global event. Everywhere we have the Paleocene-Eocene transition preserved in sediments, we see a large carbon isotope excursion. This was really an extraordinary global event. There's some additional evidence about what happened to the carbon cycle during this time. This is a site from the southeastern Atlantic Ocean, about 800 kilometers off the coast of Africa. On the y-axis, what you see is depth in meters below seafloor. And here, right around 201 meters below the seafloor, you see the Paleocene-Eocene thermal maximum. You see a large drop in the delta C13, coincident with a large drop in the delta O18, indicating a large warming event. Remember that this axis is depth, but not necessarily the same as time. Although time does increase in the sediment column, the relative time can be somewhat distorted because of changes in sedimentation rates. So you don't necessarily see the very sawtooth pattern that we did in the compilation of other cores where timescale has been taken into account. One of the unusual patterns we see here is not just a change in the delta C13 and the delta O18, but also a drop in the calcium carbonate content of the sediment. Before the event, calcium carbonate in these sediments was about 75% of the total mass of the sediment. And above the event, it's about the same, 75 or 80%. But during the actual event, calcium carbonate drops to almost zero for tens of centimeters and then recovers over another few tens of centimeters back to its original level. This is a clue telling us something about what's actually going on with the carbon cycle during this event. It was clear to the scientists who first discovered this event that the huge change in the delta C13 suggested that something unusual was happening to the carbon cycle. In many ways, it's analogous to the drop in the delta C13 of the atmosphere we observe today due to burning of fossil fuels, where burning all of this fossil fuel has released a lot of organic carbon, now turned into oil and coal and gas, that is depleted in C13, and therefore it's dropping the delta C13 of the atmosphere. In this case, we see not just the delta C13 of the atmosphere dropping, but of the entire deep ocean measured by benthic foraminifera, dropping by 3 parts per thousand or 3 per mil.